Morning, distinguished scholars and industry colleagues. I'm honored to have the opportunity to share our work at this conference. I'm working at the China Academy of Railway Science. In 2024, our paper WSSGCN was published in Neurocomputing. Today, I will guide you through our research and its applications in the railway industry. Currently, I'm mainly responsible for the Low Altitude Intelligent Inspection System, which utilizes UAVs for various tasks, including task assignment, data transmission, data collection, monitoring and tracking, and intelligent scene inspection. Well, I will introduce our work in 5 main sections. Firstly, let's move on to research background. Graph structure data has a wide range of applications across domains such as social network analysis, traffic forecasting, bioinformatics, and action recognition, to name a few. A key tool for extracting insights from these complex relationships is the Graph Convolutional Network, or GCN. A wide range of GCN variants have been proposed. However, real-world networks are often heterogeneous, consisting of diverse node and edge types. As a result, conventional GCNs may struggle to differentiate between nodes and inadequately aggregate information from distinct neighbors. However, as GCNs become deeper, they face the challenge of increased memory consumption, which eventually becomes a bottleneck. To address these issues, we propose a novel model, WSSGCN, which is inspired by human cognitive learning from Professor Jean Piaget. He developed the first major theory of cognitive development and was also a stage theorist who believed that learning was experience-based. Jean Piaget's theory of cognitive development suggests that human learning occurs in distinct stages, which offers a very valuable analogy. For example, younger learners benefit from methods like games and crafts, while older learners thrive with abstract techniques such as problem solving and critical thinking. Building on this progression from sensory exploration to logical reasoning, we propose a method that mirrors this developmental process to more effectively handle graph data. Let's move to related work. Graph neural networks were firstly introduced as a way to extend neural networks to process graph-based data. The core concept of graph neural networks, or GCNs, is to use the neighborhood of each node to define a computational graph. For example, to define the computational graph for a target node A, we first need to gather the feathers of its neighbors, node B, node C, and node D, and transfer these features to node A. This process allows us to construct a tree-like structure to store the features of each node. Embeddings are then used to represent the features of the nodes. As the number of layers increases, the node's neighborhood expands progressively. Ultimately, this structure can be formalized to capture the relationships and features across the graph. Since GNN was proposed, many variants have emerged, such as DCCA, DAGNN, GGP, etc. However, heterogeneous graphs, those with diverse nodes and edge types still present a challenge for these models. To address this challenge, techniques like message passing neural networks (MPN), graph attention networks (GAT), etc., have been developed. While these methods have shown promise in specific tasks, they often face difficulties in generalizing to diverse and dynamic real-world applications. So, GCNs become an effective way to solve this problem, but traditional GCNs face oversmoothing and representation issues. Numerous strategies have emerged to overcome these limitations. Cluster GCN segments the graph into smaller subgraphs where an innovative clustering algorithm. AGCN blends multi-scale layer combos, and ResGCN use residential connection and normalization for deep GCNs. However, these approaches are often computationally expensive. Let's move to our methods. But before we dive deeper into WSSGCN, I would like to briefly discuss our previous work on knowledge distillation. As part of WSSGCN's idea originates from this paper. Knowledge distillation is a method that uses a teacher model to train a student model, with the goal of improving the performance of the student by transferring knowledge from the teacher. In this work, we propose a weekly supervised learning framework with 3 stages: response-based, feature-based, and relation-based. These stages are combined to enhance the accuracy of the student model by leveraging the teacher model. In our framework, the staged knowledge distillation (SKD) shown in Figure A consists of 3 independent stages, each targeting a different aspect of learning. However, this method is resource intensive due to the 3 separate stages. To address this, we proposed the relevant staged knowledge distillation (RSKD). As shown in Figure B, we introduce an additional combination-based stage to reduce model complexity by eliminating parallel process. The bottom line is that SKD and RSKD mimic human learning by employing distinct loss strategy across different layers, guiding the student model's learning process step by step. Specifically, the response-based stage focus on aligning the outputs of the final layer between the teacher and the student models. The feature-based stage utilized pooling strategy to ensure feature consistency across corresponding layers of both models. The relation-based stage emphasizes maintaining the similarity of feature relations across multiple layers. Overall, SKD uses a cascading strategy to combine the 3 substages in separate models, while RSKD combines these substages within a single model, reducing the number of parameters. More details can be found in our paper published in IEEE TCSVT in 2023. Building on the success of our distillation approach, we extended this method to GCNs. In Figure A, we illustrate the traditional depth-based graph process as shown. In a depth-based GCN, the update process occurs gradually, layer by layer. Each node depends on its neighbors, and even the neighbors of those neighbors to update its features one step at a time. While effective, this approach is inefficient and time-consuming. Now, if we examine figure B, it illustrates the substage-based method we propose, which emphasizes extracting wide-spaced substage features. In the diagram, the red circle represents response-based information transfer, focusing on local information around the green node. The yellow circle indicates feature-based information transfer, targeting small-scale patterns surrounding the green node. The blue circle shows relation-based information transfer, capturing broader long-distance relationships around the green node. By integrating these three components, we can simultaneously update weights and feature matrices across different spatial scales without the need to construct a deep GCN. There are some key notations used in the formulas, and I will not detail these equations one by one as they can be found in our paper. However, I would like to emphasize that for different substages of our method, we adopt a set of hyperparameters to adjust the model's performance, such as alpha, beta, eta, mu, and so on and so forth. This forms the foundation of our algorithm. Now, let me walk you through the core process of the WSSGCN method. As shown in the figure, our method introduces a trainable white-spaced and substage kernel, setting it apart from traditional GCN methods. Unlike fixed filters, this kernel dynamically adjusts the weight of each node's contribution to the target nodes, leveraging hyperparameters to better capture local structure patterns. The process begins by extracting multiple sides of a representation matrix from three distinct substages as shown in the previous slide. These vectors are then concatenated into a single unified vector. In order to update the entire graph, the features of all nodes are aggregated and combined into a final vector. At last, it is passed through a fully connected layer for further processing. The algorithm describes the computational procedure of our method. As you can see, we initialize many hyperparameters to adjust our model. Our algorithm demonstrates both high efficiency and parallelizability. Specifically, the time complexity can be expressed as OMP. There, N represents the set of node types and P represents the set of each types. The complexity is determined by maximum value among the three terms as shown in the formula. We also compare the training time for these substages as shown in the figure. The difference in training time across these substages are influenced by complexity of feature generation and hyperparameter tuning. On the one hand, each substage involves learning to generate feature vectors for nodes and edge, a process that requires significant computation. The feature-based and relation-based substages tend to involve more parameters and computations, which increases training time. On the other hand, both the relation-based and feature-based substages often require extensive hyperparameter tuning, especially when dealing with more complex data. This process can further increase training time. This is also consistent with the human recognition procedure. Now, Let's turn our attention to experiments. In our experiment, we utilize a total of 8 heterogeneous graphs and 3 homogeneous graphs, and for model comparison, we evaluate a wide range of baseline models as shown in Table 1. To optimize the performance of our method, we conducted comprehensive hyperparameter tuning. The initialized range from each dataset are presented in Table 2. To ensure consistency and fairness, we used the original code provided by the authors for all baseline models in our experiments. Table 3 represents the accuracy of our experiment, highlighting the best performance achieved by each model, with green indicating the second best performance. We also conducted experiments on synthetic data to further verify the generalization ability of our method, as shown in Table 4. The data synthesis methods include subgraph extraction and resampling. It's fascinating to observe that as the data size and complexity increase, our methods demonstrate a significant performance advantage over other methods. We also assessed the model's accuracy across a range of layer depths from 2 to 64 layers. In contrast, WSSGCN attains convergence with just 2 layers, showcasing its efficacy for both homogeneous and heterogeneous datasets. In this slide, we present ablation studies across diverse datasets. The green highlights indicate an accuracy gain of over 5%. The experiment emphasized that wide-spaced and sub-stage structures lead to the optimal overall performance. Notably, the influence of sub-stage design is particularly pronounced for simpler datasets, while the efficacy of wide-spaced structures shines on complex datasets. We also employed statistical testing methods. Specifically, we utilized the Friedman test to evaluate overall performance among models. This indicates that our method has the top 1 average rank among all datasets. We also performed the subsequent Nermani post hoc test to compare the difference. The result of the experiment showed that the critical difference between our algorithm and most other algorithms is around 0.5. In most cases, it shows a significant difference across multiple datasets. Let's move to the final section, applications and future work. We have deployed several models on drones to carry out routine inspection tasks along railway lines, such as rail track object recognition, bridge bottom disease detection, and erosion monitoring. Traditional human-based detection methods are not only resource-intensive and time-consuming, but also often fail to identify subtle issues. To address these challenges, we are optimizing our models to overcome these limitations. In the long term, we also schedule to leverage technologies such as 5G, big data, and artificial intelligence to deeply integrate with complex railway scenarios. Our focus is on developing key technologies for drone flight control, intelligent recognition, and data processing. This will drive innovation in railway drone technology and promote industry transformation and upgrading. Well, we believe that there is still further work to be followed. Firstly, WSSGCN in weekly supervised learning will enhance the representation learning of GCN models, potentially addressing many challenging problems in real-world applications. Secondly, due to the high cost of hyperparameter tuning, incorporating attention mechanisms into WSSGCN could prove beneficial as it would help the model generalize more effectively across a wide range of datasets. To wrap up the presentation, we propose a novel approach called WSSGCN, which utilizes both stage-based and wide-based methods. We conduct extensive experiments on both homogeneous and heterogeneous datasets, demonstrate that it outperforms state-of-the-art methods in classification tasks. Well, that's my presentation. By the way, I'm actively seeking collaboration opportunities to further my research in deep learning. If you are interested, please feel free to reach out to me via email. Thank you for your attention.